So in the previous section, we saw how integrator can be created using an accumulator, and then we applied that accumulator to calculate the integral of a line. In this section, we are going to use the same accumulator and conduct integration on a cosine signal. So let's start by defining the signal parameters. So my signal is going to last for 1 second, so I'm defining the time duration here, and the sampling frequency will be 1000 hertz, which means that my sampling time dt, which is nothing but inverse of sampling frequency, and then I have to decide my signal's frequency. So let me call it, and let's say it is a 4 hertz signal, and I will also define the amplitude of this signal. Let's say it's 1 volt. So let me first generate time axis for the plotting purposes. So how I'm going to do it is that I'm going to generate make a variable called t, and then use a function called arange. It says so from where do I want to start my time axis? I want to start it from 0, and I want it to be for 1 second long. So I'm going to take it to 1 second, and in how many steps I want. So it'll be dt, the sampling time. So let's have a look at how this time series looks. So here we are starting from 0, and we are going to 1 second, and our dx is 0.001. So our first step is 0.001. If you see here, we have 1 divided by 1000 is 0.001, which is the sampling time. So we've been able to generate the time values of the signal. So now we create the cosine signal. So I'll call it cos input signal, and how I'm going to generate is using this function called np.cos, and 2 into pi 2 pi ft, which is frequency, into time. So this is what is my cos signal. So let me just plot it and see if it's working or not. And also I will activate my general plot settings here. Okay, so we'll just plot this cos signal, and we can see that we have successfully created a cos input signal. It starts from 0, it goes till 1, and since we had kept the frequency at 4 hertz, we can see 4 waveforms here in 1 second. So far so good. So what we now want to do is to integrate this signal and using the accumulator that we had created earlier. So how I'm going to do it is that I'm going to create my output signal, which is going to be, hopefully it's going to be a sine, and I'm going to again put it through my accumulator and pass on the input signal and multiply it by step size, which is the sampling time. And this time I again plot this. So here we are, the blue line is the input, and which is cos, and we can see that the sine signal does get generated, but it is very small in amplitude. Why this is happening is because we have not taken the gain factor into consideration. So the gain in this case will be, we just need to amplify the signal by gain factor, and the gain is 2 pi into frequency. And now let's say we take the same signal, sine out, and we apply gain to the signal, and let's plot the signal again. So you can see there's a green colored signal, which is the amplified version of this orange signal. Orange signal is before applying the gain, and the green signal is after applying the gain, and you can very clearly see that it's a sine signal. The integration has taken place. The integral of cos, which is this blue line, is a sine, and the sine is depicted by this green plot. So let me just make it more clear. Let's say just 1 hertz signal, and now you can clearly see. So this is the cos signal, and the green one is the sine, which is the integrator output after getting amplified by the gain factor. But we know that there's a DC term. Output of any integrator is the integral plus C. C is the DC term. Let's say if it plays any role in this experiment. So let's do one thing. Let's just disable one plot, and let's try increasing the frequency. Let's say it becomes 30 hertz. So you can very clearly see that the blue signal is the cos signal, and the sine signal is orange one, and it is DC shifted. It is going up, as you can see here. The effect will be more prominent if I increase the frequency further. Let me just make it say 50 hertz. So you can see here that there's a DC shift that is happening to the output of the integrator, and why this is happening is because we have not considered the C term, which is always added to the output of an integrator. So here we have to basically cancel out the DC component in this signal. So the DC component is nothing but the average of the this output. So I'm going to calculate the output as NP mean, and pass on this sine out signal, and then I'm going to subtract this from the original output, and once again generate the plot. So if you remember, our before we run this code, our signal was DC shifted, and now we have corrected it for DC shift by subtracting the mean from the signal. Let's see how it looks now. So now you see that the DC shift has gone, and the signal is absolutely perfect and matching the input. So let's just go back once again and reduce the frequency to say 2 Hertz, and there you are. So the integrator is working beautifully. It has converted the cos signal into a sine signal with the same amplitude. So now let's also generate the theoretical or the analytical result. We know that the output of or the integration of a cos signal is sine. So let's generate that sine here. Let me call it sine theoretical, and I'm going to use a function called sine 2 into pi into frequency into time. So this is our theoretical result of integration of cos, and let's see whether this signal is overlapping with the output of the accumulator to verify the functioning of the accumulator. So there you are. Actually, they are overlapping, and you're not able to see it. So let me just disable these plots, and activate my other plots here, so that you can. I have one more plot somewhere here, so I need to disable this, and then let's see. So here we are. What you're seeing here, let me just also activate the legends so that you can clearly see what's happening. Okay, so the green signal is the cos input, which you can see here. It's a cos signal that is being applied to the integrator. The sine out is the output of the integrator, the blue, the blue line in this plot. And then sine theoretical is the red dashed line, which is perfectly overlapping on top of the output of the accumulator, which means that the output is, which means the accumulator is conducting the integration perfectly. And now we see what all can be done using this integrator. So let me generate some noise and add it to the input signal and see what integrator does to this noise. So let me just define some noise. I'm going to generate Gaussian noise or normal noise here with the 0 mean and say 0.1 standard deviation. And how many number of points that I want to generate? I want to generate as many points as there are on the time axis. So this is my noise, and now I want to add this noise to my signal. So my signal out of the accumulator or the integrator was sine out. So I'm going to take the same signal and add noise to it and plot everything once again. Or I have to, sorry, do it with the cos signal, the input signal, not the output signal. So I have to add it to the input of the integrator, not at the output. And this is cos in, not cos out. So there we are. And I'll disable the theoretical results here so that you can see the output of the integrator. So here we are. So you have a look at what's happened here. Our input signal is a cos signal, which is extremely noisy. There are high frequency components on top of it. And when we pass it through the integrator, there's a 90-degree phase shift because of the integration action. But the signal eliminates, the integrator eliminates the entire noise, and we get a very clean output back, almost as clean as the original signal. So what you can conclude from this is that integrator acts as a low pass filter, and any high frequency component which is depicted by this random noise riding on top of this low frequency 2 Hertz signal, it is blocked by the integrator. It is blocked by the filtering action of the integrator, and in general the integrator acts as a low pass filter. So as we have seen that integrator acts as a low pass filter, the real world application is implemented, the simplest implementation is through a RC integrator, which consists of one resistor and one capacitor. As you are aware, the capacitor acts as an accumulator of charge or an accumulator of voltage. And this is exactly what is the purpose of accumulator that leads to the integration action. So all the integration signs that you're seeing here essentially are because the capacitor has the property to accumulate voltages. Now, how fast or how slow that is done is decided by the values of these two components, RC. And practically for the low pass filtering action or for the integration action, the values of R and C are very large. And RC decides the time constant of this capacitor. The larger is the time constant, the longer is going to be the response time for this capacitor to respond to the input voltage. So if you see, if any input voltage is applied here, we get an output voltage, and that output voltage, if you see the last formula, this output voltage is nothing but a integration of the input voltage multiplied by some gain factor, and that gain is nothing but this RC. This RC decides the time constant of this filter, and basically there is a high frequency signal noise on the incoming signal. That means it's fluctuating really fast. So the filter is made, or the capacitor is made insensitive to those fluctuation by making its time constant large. So this R into C, both these components, since they have very large values, the RC is large and the time constant is large, and time constant decides the response time of the filter. Since the response time of the filter is very large, it will fail to respond to the high frequency components of the signal, which is noise, and hence the noise will get eliminated, and you will get back an integrated version of the input signal. So in the demonstration in Python, we showed that the input signal was cos with some noise component, and what we received out was the integrated version, that is sine signal, but the noise eliminated. So this is how practically integration is used in signal processing.